So, boiling. What exactly is boiling? And at what temperature does the liquid start to boil? Boiling is when you see the bubbles form in the liquid, inside the liquid, and rise up to the surface of the liquid, releasing the gas inside those bubbles. You see, you can put a pot full of water to boil on your gas stove, turning on the gas, but initially it will just get hot. At some point it will start to bubble up, and you know you have arrived at a point where it's boiling. Water at room temperature 25 degrees Celsius is not warm or cold, and then you start heating it up. It goes from 25 to 26 all the way to 100, and at 100 degrees Celsius boiling happens. That's the boiling point for water. Different liquids may have different boiling points. But why does it boil exactly at 100 degrees in the case of water? And what exactly is happening when it's boiling? Well, we just learned about the vapor pressure. And at boiling, at the boiling temperature, the vapor pressure of the liquid equals the atmospheric pressure. Now, whenever we boil a liquid, we never boil it in a closed container. So the container is open. You don't ever in a lab as well boil a liquid in a closed container, because the vapor pressure can cause crack in your glassware, and that's very dangerous. When you are open to the atmosphere, what is the atmospheric pressure? The atmospheric pressure is 760 millimeter mercury. As you are boiling your liquid, more of that liquid enters in the gas state, and so the pressure, the vapor pressure of that liquid starts to rise. At some point it will equal to 760 millimeter mercury as well, which is equal to the atmospheric pressure. That's the point when boiling will start to happen. So normal boiling temperature is measured at 1 atmosphere. Now if you were to go on a mountain, the atmospheric pressure is less than 1 atmosphere, because you have less air on your head from the top of the atmosphere to the mountain where you are standing. So it's less than 1 atmosphere. Hence, it could be something like 500 millimeter mercury, and so your water will start to boil at a much lower temperature. Anybody who lives in a higher altitude is aware of that. Similar to that, if you live in a lower altitude, the atmospheric pressure is more than 760 millimeter mercury, and so boiling point will rise. So that's how boiling of a liquid is related to vapor pressure. Finally, the exact boiling temperature depends on something known as intermolecular forces of attraction in the liquid. Liquid water boils at 100 degrees Celsius, but drinking alcohol, for example, if you were to boil it, it boils around 80 degrees Celsius. What exactly governs the temperatures in that case? So if you have alcohol, its vapor pressure will reach the atmospheric pressure around 80 degrees Celsius. On the other hand, liquid water, its vapor pressure will reach the atmospheric pressure at 100 degrees Celsius at sea level. So the intermolecular forces of attraction, there are two types. They are called dipole-dipole interactions, or London dispersion forces of interaction. London dispersion forces of interaction work in non-polar molecules. Well, actually they work in all the molecules, but they are primarily present in non-polar molecules, because non-polar molecules cannot have dipole-dipole interactions. Now they are temporary dipoles, and they are very weak. As the size of the molecules increase, the London dispersion forces of attraction increase, and so the boiling point goes up. So if you have a large molecule and you are trying to boil it, its boiling point will also be higher than a small molecule, because of London dispersion forces of attraction. Now dipole-dipole attraction is much stronger than London dispersion force of attraction. Dipole-dipole interaction or dipole-dipole attraction is between polar molecules. So a polar molecule has a positive end and a negative end. One molecule's positive end is attracted to the negative end of another molecule, and this attraction, if it goes up, the boiling point will go up, because whenever a liquid boils, it must break those attractive forces that is keeping it in the liquid state. And in order to break that attraction, you have to supply heat. The greater amount of heat you have to supply if the attraction is high. Finally, there is special kind of dipole-dipole interaction known as hydrogen bonding. It's not considered a van der Waals force of attraction. It's a special kind of dipole-dipole attraction. It's very, very strong. As a matter of fact, it's primarily responsible for the high boiling point of water. Now, what exactly is hydrogen bonding? Well, it happens in the case of oxygen, nitrogen, and fluorine. Those are the three atoms where it works. The atom that is participating in hydrogen bonding is hydrogen itself. Now, here is a molecule of water. The red ball here represents oxygen and the white ones represent hydrogen. One of the hydrogens on a water molecule is attracted to an oxygen on another molecule, and it's making a bond with it known as hydrogen bonding. It's actually bonding with the lone pair of electron on the Lewis structure of oxygen, of Lewis structure of water here, where oxygen has one lone pair and there is another lone pair on it as well, which is making a bond with another hydrogen here. So these are the kind of interactions present in water, raising the boiling point of water to such a high degree. If you compare this to gasoline, for example, gasoline is a non-polar molecule, is made up of non-polar molecules. So it doesn't have any hydrogen bonding in it. So it boils at a very low temperature. Gasoline molecules reach a vapor pressure equal to atmospheric pressure at a very low temperature, a little bit higher than room temperature. So if you spill some gasoline at the gas station, at the pump, you will see it evaporate very quickly. On the other hand, water takes its time. Now, hydrogen bonding is present in hydrogen that's directly bonded to an oxygen, or hydrogen that's directly bonded to a nitrogen, or hydrogen that's directly bonded to a fluorine. And it can only work if the other atom to which it's attracted to is also one of those three, either oxygen, nitrogen, or fluorine. So here we see attraction of a hydrogen that's directly bonded to an oxygen being attracted to another oxygen. It could have been a nitrogen or a fluorine, but not any other atom.